Hi everyone, welcome to part 3 of 0 to 8086 playlist. And in this video we are going to talk about binary, the language of the machines. If you haven't subscribed to the channel, please do, because we will be moving ahead with this playlist and soon we will be finishing up the 8086 microprocessor and how it works. So let's get started. So binary is also known as the language of the machine. But why is it called binary? It's because binary, the word bi, means of two states, such as a tri means 3, bi means 2. So binary has two states, one being 0 and 1. These two states can be represented as true or false values, on or off, or any way you want to represent them. We are not exactly familiar with the binary system. The number system that we used is decimal, which is also called the base 10 number system because deci means 10. That's why it's called of 10 states. The number system ranges from 0 all the way up to 9. It has around 10 states to represent all of the numbers here. But computers do not exactly understand all of the states. It runs on electricity, so the binary is the best language for the computers because the presence and the absence of electricity can be represented as 0 and 1 in binary, and thus it can be controlled by the transistors, and thus the electronic communication can happen in the computer. Okay, so moving on. With the example of our decimal number systems, the number 224 can be represented as tens. We can see there are like two digits. There are like 3 digits, one being the 2 hundreds, the 2 tens, and the 4 ones. This is represented in this block. As you can see, we have 4 ones, 2 tens, and 2 hundreds. So if you add them all up, 2 hundreds, the literal way, and 2 tens, and 4 ones, adding all of them up can be 224. Similarly, in the binary, the number 101 can be represented in decimal as ones, twos, and 4s because it is at base 2 number systems. This 101 is the number 5 because, as you can see, we have got 4 ones plus 1 ones here and here, and 2 zeros which are not exactly added up. And adding this all up, the number 101 represents the number 5. So this is how binary numbers can be represented as decimals, and this is how these are counted. If you might be asking, what if there were more digits? Like instead of these 3 here, What if there were an addition of 1? So suppose similarly, if we add another like 3 here, we would have to add 3 in this box, and also we need to increase the tens by 1000. So here, as this is a base 10 number system, this increase is a magnitude of 10, 10, 10. And as binary is a base 2 number system, this increase is of base 2. So 1 becomes 2, 2 becomes 4, and 4 becomes 8. Then comes 16, 32, and it continues. Later on this video, we will know how to calculate these things more efficiently. Okay, moving on to the addition of numbers. In this section, we will also give the examples of decimal numbers and how they are represented. So the addition of decimal numbers are done by like simple calculations that we learned in our elementary school. The 9 plus 3 is, we know that 3 plus 9 equals 12, but this 1 is an extra. So we write 2 here, and the 1 gets carried out here. Now that we have 1 plus 8 plus 1, which is 10. So the 0 comes here, and the 1 gets carried over to here. Now the 1 plus 1 is 2, so the answer is 202. So we do understand the carry, the concept of carry when it comes to addition in decimal systems. Similarly, the concept of we will use the concept of carry in binary addition as well. Suppose these two numbers in the binary section, this number represents 183, and the below number represents the number 19. So adding these two up is 1 plus 1. We know that 1 plus 1 becomes 2, but there is no 2 in the decimal, in the binary. So 2 is represented as 1, 0. So we give the 0 here, and the 1 gets carried out over to here. Okay, let me just clear this up a bit. Okay. So we write the 0 here, and the 1 gets carried over to here. So we know that 1 plus 1 plus 1 equals 3. But the 3 in decimal, the 3 in binary is 1, 1. So we write the 1 here, and the 1 gets carried over to here. 1 plus 1 is 2. We know that the 2 is 0, 1. So 0 becomes here, and the 1 goes carried over to here. So we do this simultaneously, and we find that the 1 gets carried over here, and the 1 plus 1, 0, 1 gets carried over here, and this one and this one. So we'll see that this number equals 202 in decimal, similar to this problem. So addition in binary is similar to addition in any other number systems. So let's move on to what is called a byte. The 8 bits, a single digit of binary is called a bit. 1 bit can be either 1 or 0. So it can hold two values. 8 bits is very common in binary, so it is called a byte. A byte can hold a maximum of 256 values, with all ones being the maximum and all zeros being the minimum. Likewise, 1000 bytes becomes a kilobyte, 1000 kilobyte becomes a megabyte, 1000 megabytes becomes a gigabyte, 1000 gigabytes becomes a terabyte. We'll see all of these bytes and bit notations, mega, giga, and tera later in this video. Now, how are we supposed to convey negative numbers? But before that, I want to clarify one thing. We normally represent numbers, like if you want to represent numbers in like 8 bits, we can hold a value of 256. So an 8-bit can represent 256 different values. So how can we, like, is it enough? That's the question. So for like more calculations, this is actually not enough. That's why we use 32-bit numbers, exactly not number system, but 32 bits for storing numbers. So here in the negative number section, we'll see that how the negative numbers are stored. Normally, we know that they are negative numbers. So as in the previous section, we saw that the maximum value of 8 bits can be ranges from 0 to 255 or 6. Like 255 is the value if you consider 0. So this is the range of numbers that it can hold. But what about if I want to say -1 or -256? So this is where comes the concept of negative numbers in binary. So negative numbers are represented by the first digit or first bit of a binary number. Suppose which we give the signs, the plus or the minus, before the digits in our decimals, like for example +/-19. The first bit is given as the sign. That is the one for negative. If it is 1, then we will consider the number being negative, and if it's 0, we'll consider the number being positive. So this goes the concepts of negative numbers. But what about if I want to represent something like a 3.34? How would this point be dealt in binary? So then came the concept of floating point numbers. So the floating point numbers normally use, as I've said before, 32 bits to represent all of the possible numbers. Supposingly, the first bit is used for the sign. These 8 bits are the exponent, and this is called significant. But what are exponents and significance? If we look at this example, this number is this one. It is representing a floating point number. So if we write this floating point number as like this, which is the similar, this part is significant, and this part is the exponent. So that is what we are representing by the 32-bit numbers here. But what about text now? So the most common conventions of representing text by binary numbers is ASCII, which is the American Standard Code for Information Interchange. If you haven't heard about ASCII, you're going to learn how it was invented now. In the 60s, 5 bits was enough to represent all of the characters, like A to B, A to Z. So that is around 26 values. So 5 bits were enough because 5 bits could hold 32 values. But later, when ASCII was invented in 1963, it could hold 124 values, 128 values, because it used 7 bits. So this was enough to hold A to Z, the lowercase, from A to Z in capital numbers 0 to 9, symbols, and etc. Because 224 values was a lot. But later, the ASCII was extended to 8 bits, giving a total storage value of 256 different characters could have been stored. So now I'm going to show you the extended and the original ASCII table, which has all of the values we use every day. As you can see, that in the first column here, these are called ASCII control characters, which were of 31 or first 32 values, which has the special characters such as the backspace or the space or the enter key or the next line. Those kind of characters were stored in the first 32 bits, 32 places. Then the printable characters, which is the alphabets, the smaller alphabets, then the special symbols, the numbers. These were stored in from 32, value number 32 to 126. Later, when the extended ASCII characters stored Latin values, the Latin characters, and then more special symbols like a half or these characters or whatever these means. And yeah, so this could hold all of the values known to computers, but also these were not enough, because in separate countries they had separate symbols or separate characters to represent their own language. So to unify all of the characters, the last thing that was invented in 1992 was Unicode, which used 16 bits to represent the numbers. 16 bits could hold 2 to the power 16, which is 65,536 values, which could hold all of the numbers in all countries, and special characters such as the Chinese character, the Japanese characters, also in Bengali, Hindi. Those characters are also in the Unicode list, and also it could store emojis with other emojis. So this was a very the Unicode unified every notation and representation of all numbers. Now, the last part of the videos, I would like to share my way of remembering all the powers of 2. Well, if you're a computer science student or trying to learn about computers, this would be a good table for you to not exactly memorize, but keep in your mind. Now, okay, so how do I remember all this? The first thing that you have to remember is that these things are just the powers of 2. The first column are just doubles of each other. We know that anything to the power of 0 is 1, so we write 1 here, and we just double it up. 2 to the power 1 is 2, then 4, 8, 16, we just double it up. 32, 64, 128, 256, and 512. So this column is the thing that you have to memorize first. Later, what you have to memorize is the first row here. The row has the number, the first number here represents, if it's 1, if it is 2 to the power 10, it's gonna be a kilobyte. If it's 2 to the power 20, it's gonna be a megabyte. If it's 2 to the power 30, it's gonna be a gigabyte. And you guessed it right. If it's 2 to the power 40, I can say easily that it's gonna be 1 terabyte. And what about all of the middle numbers here? The middle numbers are a combination of these and these. So if you're in an exam, or if someone asks you what is the number of 2 to the power 25, you know that if it's 20 if it's in the range of 20s, you know it's gonna be megabyte. And if you know like the 5 is 32, so you can easily say, pardon, you can easily say that it's 32 megabytes of space. If anyone says like, what is 2 to the power 48, you can easily say that the 40s are of terabytes and the 8 comes from here, which is 256. So it's 256 terabytes, which is a very big space. So rewind this video and you can take the screenshot or you can write it down if you want. But this is how I remember, like try to remember all of the powers of 2. And this helped me a lot in my exams and like in other interviews as well. So that's it for this video. In the next video, we will discuss about more exciting things about logic gates, how the binary representation of AND gates and OR gates are formed. So I'll see you in the next video. Thank you.